Laplace transform. And for the Laplace transform of the flux concentration, we also saw that since it's a Laplace transform, it's also a moment generator. So what it allows us to do is essentially calculate moments in time, just saying within this involving means of n. And what we do of means of n in this context is e to the power of n. All these are temporal moments, because they're moments in time. These are just the time axis. And basically what we said was one of the very cool results, important results for us was, so our nth moment, we essentially defined it in this terms. Right? And what we said was by taking derivatives of this with respect to s and setting s equals to 0, we are able to recover the nth moments. Okay? And what we also did is, when we were looking at various models, we essentially found expressions for C f hat. We also found expressions for the bulk concentration and its transformation as well. So these are going to be useful. One of the things that you will notice is that we had that g of s function. And we said as the models become more and more complex, that is the only part that is changing. Okay? So when we are trying to find moments, especially using the Laplace transform over here, what we are interested in is computing quantities, for instance, okay, and we could write this as dc. For the first moment, we would be trying to set things equal to 0. This quantity does not change with the models. dg ds keeps changing. Similarly for second derivatives and so on. Okay. So very useful, because otherwise trying to evaluate this quantity would first require us to have an expression for Cf of x of t, which means we would take the original differential equation, somehow find that function, then be able to integrate it with respect to n and get an expression for this. That would be very complicated. Perhaps we could do it for the advection dispersion equation, but if we start adding physical non-equilibrium, mobile, immobile model, other complications, the solutions are not very easily available. But using Harris's method, using the transform, we are able to get to it much more easily. You will notice then that the 0th moment, by this definition, is simply the area under the curve. Okay? The first moment, which is in terms of time, essentially physically says whatever the centroid is of this shape, it will give us this distance. Something that we think of as mean, the time, mean travel time kind of an idea. And then the second moment would essentially say something about the spread of this shape around the mean, or we can calculate those. What I want to do is sort of introduce you to another idea, which is perhaps more fundamental. We can do other things with that, including what we do for the advection dispersion equation. So let's start talking about travel times. And here I want to motivate our thinking in terms of linear systems theory. Much of what we do, whether it's solute transport, as long as the equations are linear, when you do unit hydrograph, when you do many other problems, we are essentially using linear system theory, which essentially says, I have a system, whatever input signal that I provide, whether it's water, heat, solute mass fluxes, and so on, the system is going to transfer it and I'll recover an output signal. Okay? And if the system behaves linearly, then I'm able to do this very efficiently. Okay? Including, for instance, finding the flux concentration as a function of time, which would be my output signal for a delta input of solute in the inlet n. Okay. So what we now want to do is sort of use a different conceptualization. Let's say we still have that soil column. Okay, this is a sketch, and this is the inflow N. We will assume that the flow rate is steady. So Q, the total volumetric flux through the soil column, is steady. It's not changing with time. So Q is the amount that's coming in. What is entering at this is a certain amount of solute, which is our flux concentration at x equals 0. And at x equals L, what we collect is the flux concentration, which would look perhaps something like this. Okay. So what we now want to do is think about this as if I have a large number of solute particles, and individually we will assume that they are countable. We don't have to, but the explanation is easier if we start that way. So each of these particles is essentially traveling through our system. Even though our straight line distance is L, each of these particles is going to take some arbitrary path and eventually come out, right? And that is what is happening when we introduce solute at the inlet end. It goes through, and then some of it comes out, in time. So our conceptual experiment, which we want to do is, let's say in this flow field, which is steady, we release a large number, capital N, of solute particles. Okay. At time t equals 0, we release them. Each of them, let's say for convenience, has a mass of small m. Okay. And each of these are instantaneously released at the inlet end. Okay. What we start doing is, at the outflow n, as a function of time, with each delta t time interval, we'll collect the water that comes out, count how many particles we have of the solute in it. Go to the next delta t, collect that water, and count the solute particles, similar to what we do in experiments. Okay. So what we'll do is collect these particles at the outlet port at delta t time intervals, and we will denote by n sub j as the number of particles that I have collected during the jth time interval. And eventually, if it's a conservative solute, okay, what we expect is, if we wait long enough, if we continue this experiment long enough, all these capital N particles, I should have recovered them at the outlet end. Okay. After that, since I have not added any more particles, I'm not going to see any of those come out. Okay. So the total mass of solute then that I have added is small m times capital N. Capital N was the total number of particles. M is the mass of each particle. Let's say that is what we call as the mass of solute that we introduce at the inlet end. Okay. So very simple experiment. In fact, this is going to be your tutorial problem today. Okay. So then what we do is we essentially prepare a plot. And what this plot is saying is, this is time in delta t time intervals, 1 delta t, 2 delta t, 3 delta t, 4 delta t, and so on. And this bar height over here shows the number of particles that were recovered in those delta t time intervals. Okay. So that if this is my jth time interval, the volume of water that I collected was Q times delta t, because Q is the flow rate, that is steady. Q times delta t is the volume of water. With that water, we collected n sub j particles. Okay, and therefore the mass of solute that we recovered is m times n sub j. So far, it's fairly simple. So what we now want to do, remember we talked about random variables, and Professor Guha was introducing this. So what we want to treat is, when we look at this, what we think is random is the travel time of the particles, because we introduce all of them at time t equals 0. Some of them are arriving earlier, some of them are arriving later. If I think of the travel time, I will treat that as a random variable. Okay. So some of these travel times are smaller, some of these are larger. Okay. So I'll denote capital T as my random variable, that is the travel time. So basically my flux concentration, which is a curve, I think of this as a surrogate for the travel time distribution function. Okay. And I will also denote T sub j minus half, which is essentially halfway between this interval j minus 1 delta t to j delta t. And during that time, remember we defined our flux concentration. And we said the flux concentration is whatever mass flux has come out divided by the water flux. So in a time interval delta t, if I measure my flux concentration, n sub j times m was the total mass of solute that came out. The volume of water that I collected was q times delta t. So that is my estimate of the flux concentration, right? That is how we have defined it. So if n sub j particles came out during this delta t time interval, out of a total of capital N particles that were added, okay? So my estimate is, and you must correct this in your notes, this is supposed to be j minus 1 delta t less than capital T less than j delta t, not the other way around, okay? J should not be less than j minus 1. So what I want to do is interpret this ratio, n sub j over capital N, okay? It's a fraction. The fraction of particles that were recovered during this delta t, jth delta t time interval. So I interpret that as, this is my probability density function multiplied by delta t gives me the area under that curve, and I want to equate that probability to this ratio, n sub j over n, because that's how I define my flux concentrations, okay? So far it's all fairly straightforward, but the big translation that we have made is we are now thinking of in terms of capital T, the travel time in the system. So if n sub j over n is this quantity, f sub t, then what I also notice is, therefore I have an expression for this, okay? This is my travel time PDF value. So f is essentially n sub j divided by capital N times delta t. What I measured was c sub f, that also has n sub j divided by delta t, so I can substitute that and I get this expression. Okay. So what that tells me is, if I'm computing the flux concentrations, if I want to relate that to the travel time distribution or probability of travel times, this should be my expression. And the other part is a very simple, is a basic simplification. If delta t time intervals were very small, notice that this n sub n times delta t is over here. I have m times n. M times capital N was the total mass. Q remains. This essentially becomes simply C of L comma T, because we have made delta T very small. And this is simply the travel time density at that point. Okay. And based on knowing M over Q, for this M over Q, again integrating this is the same as integrating this function from 0 to T. So this is essentially the Riemannian sum for this discrete quantity. Okay, so what we have essentially done is conducted this simple experiment where we basically at each delta t time intervals collected the water, collected the solute particles, found the mass, constructed this histogram. From this histogram, that means knowing n sub j and therefore knowing n sub j over n, I'm able to compute what the probability density is, and that is what I have plotted over here. So this experiment therefore allowed me, from knowing this, concentration flux as a function of time, to figure out what the travel time distribution is. Okay. Any questions? Okay. So this travel time distribution then is what I treat as a fundamental property of the system. So with this I can basically do any other calculations that I may be interested in. This has many names. It's sometimes called as the impulse response function, because this is the response you're getting for an impulse input. You added all those particles in one single instant. It sometimes is called as a residence time distribution, because this curve is telling you what is the time that a particle resides in the system. When it's introduced at time t equals 0, when does it come out? Okay. Or travel time distribution. Sometimes solute lifetime distribution. All of these various names for the same thing. Okay. So what we notice then is, if I have this curve CF, I have used x over here. So if x is set to L, I have this curve. If I have a certain mass of solute I am introducing, and I know the flow rate through the column, dividing all these values by m of q will actually convert this to a probability density function of travel times. Okay. So this is also part of your tutorial. So with this, introduction then we are able to do a few other things. But before I proceed, I want to talk a little about the idea of stationary residence time distributions, because you will hear this quite often. So what I'm showing is essentially the same column over here. This axis is time, and we also are hoping for some other things to work out for us. So this axis is time. Let's say at the inlet end, T in at 1 is at the first instance, I introduce a certain mass of solute. And then the residence time distribution that I got for this when I introduce particles over here looked like this. Okay. In time. Then later on, at some other time, I introduce the same mass of particles at time t2. And this is my travel time distribution or residence time distribution. If these two are not similar, then we don't have a stationary system. What it means is my travel time distribution of solute particles depends on when the particles were introduced. Okay, which means it's not stationary, though that property is changing with time. Then it becomes a more complex problem. It's a transient problem. In fluid mechanics, it's a non-stationary system. Okay, because then your travel time distribution is going to be conditioned on tau, which it will be dependent on tau. Tau is simply the time since the particles were introduced. Okay, but it's going to depend on T in, when those particles were introduced. Okay. Then it becomes a little more complicated. On the other hand, we talk about what is called as fully developed flow. If this distribution over here, if particles are introduced at this time, this is the travel time distribution. At some other time, this is the travel time distribution. That means when tau is t minus t in t when the particles entered, this is tau minus t when the particles entered. This tau value is the same. These ordinates are the same. That means the travel time distribution is not dependent on when the particles were introduced into the system. That's a stationary system. For that to happen, typically we have to have steady flow first. If the flow is unsteady, we cannot have this. Then we essentially have to use a much more complicated formulation. Okay. So we will assume that we have fully developed flow, so that our travel time distributions or residence time distributions or what have you, they're not going to be changing. They're invariant with time. So that shape of that distribution doesn't depend on when the particles were introduced. Then we can do quite a few things. Any questions? All right. Let me go to the next slide. So this is essentially building on some of those similar ideas that we see for residence time distributions. So again, this is Z is, let's say, an axis. L is the length of the column. The flow rate Q is constant. If the inlet concentration, okay, this is time. So at x equals 0, if all of it is coming as a delta function, notice that I now multiply by m over q. M over q would essentially convert that to a probability density function. Okay. And what I observe at L looks like this function. Then by definition, this function, because we had this m over q, and I think when we were deriving these equations, we set m over q equal to 1, just for simplicity. These two would essentially be the same then. Similarly, if instead of all the particles being introduced, if we maintain them at a constant concentration, what you would observe at the outlet is this S-shaped curve, which is what Professor Srivastava was showing you initially. Different boundary condition in the flux. Okay. So it's a constant times a Heaviside function, and you would get this. What you would essentially get is the CDF, the cumulative distribution function of this probability density function then. And that would be our interpretation. Okay. So all of this essentially follows. So what we have over here is simply the same thing, that if at the inlet end, delta T means instantaneously I'm adding a mass of solute M, I divide that by Q, this thing is actually a probability density function, except that all the probability mass is concentrated at T equals 0. Okay. By the time it comes out, that probability density is going to change its shape and look something like this. Okay. And this is simply saying that mass has to be conserved, and therefore the first travel time moment is this quantity, which is essentially measuring what the centroid of that shape is going to be. Any questions so far? All right. So now let's come to the advection dispersion equation. Okay. So what we now know is if I conducted an experiment, just like you are going to do in your tutorial, or you're looking at, and you have this curve for the flux concentration. So this is what you are working with now. Okay. I first assume, since we have been talking about it, is that what is occurring in the soil column can be described by this advection dispersion equation. Okay. So this is the equation, this is the boundary conditions we have been using. We select M over Q equal to unity so that we don't have to divide and normalize it equal to 1. But that's what it does. What we found was that our expression for C sub F, in this case we were able to essentially take the Laplace transform, find its inverse, and essentially get this expression. Okay. So this is our model then. This is our model for what the travel time distribution is at a distance L as a function of t. And if I have observed this under the boundary condition that I showed you, and if I divided this by M over Q, this is my mathematical model trying to represent this curve. Okay, which means I can then proceed to try and estimate quantities like D or V or whatever I want by trying to fit this curve. And like I said, V ideally we would like to get separately. Okay, but in principle, if this is my model for the travel time distribution, I have two parameters, L and D. If I did not have the advection dispersion, V and D, if I did not have the advection dispersion equation, if I simply had this mathematical function, I wanted to fit this, I would essentially use this. And I would be able to essentially find D and V. L is known. Okay. And knowing this, my expression for the nth moment would look like this, because this is the probability density times t to the power of n. And if you could evaluate this, and set, for different values of n, then you would get the moments. And then we said, oh, that's going to be fairly tedious. Not even sure I can do it. What we did do was, under this condition, we found out what the Laplace transform was for this function. Under this boundary condition, setting m under this boundary condition with m or q equal to 1, we said, hey, this is our Laplace transform. And what we know from its moment generating property is I can find the expectation as the derivative of this with respect to s multiplied by -1, set it to s equal to 0, and that should give me my first moment L over V. Okay. Similarly, I can take the second derivative of this Laplace transform, that is d square c ds square minus 1 to the power of 2, so that's 1. Again, set it to s equals 0, we get this as my expression for expectation of t square. And since capital T is a random variable, travel time, I know expectation of t square, I know expectation of t, so I know what the variance is of this travel time distribution. Okay. So a couple of things that I want to now stop and ask you. If I am given this function, and let's say I'm given data which essentially show this function, I ask you, how are you going to estimate the parameters V and D? L is known, that's the length of the column. So what are your choices? What's that? Newton-Gauss regression. So regression, any other choices? What are the two popular methods for estimating parameters? In probability theory, or well, wherever in fact, how do we estimate parameters of a distribution? Two methods. Maximum likelihood and method of moments, right? Okay. So in this context, what would be maximum likelihood estimation? So remember, we have this expression, we are trying to estimate V and D, and we are given this curve. What is equivalent to maximum likelihood estimation? That is a less obvious answer. So basically, like you were saying, if I take this function and basically do minimization of square of errors and so on, and find the V and D such that the observations and this curve look very good after doing some optimization, that is equivalent to maximum likelihood. It's essentially finding the likelihood of what values of V and D will fit the data as closely as possible. The other one was method of moments. Okay. What method of moments then says is, I have this curve, I have this data, I know its probability distribution function. If I can estimate this first moment from the data by numerical integration, I'll know where the first moment is. I can actually do this and find where the second moment is as well, right? All I'm doing is numerical integration of this curve. So it's one shape. I can use this expression over here and actually find what those are. So I would have found what the experimental moments. Experimental first moment, experimental second moment. I could then equate those to my theoretical first moment and theoretical second moment. And with these two equations, I would have two unknowns, D and V. I could estimate them. So that would be my estimate of D and V by method of moments. Is that correct? So since we are using moments, since we are calculating moments all the time, we will use method of moments. Okay. Both these methods have their advantages and disadvantages. What do you suspect is the biggest advantage with method of moments? Okay, this is something that will perhaps become more clear to us maybe tomorrow when we actually start talking about temporal moments in more detail. Okay. But method of moments does bring in some advantages. It has some disadvantages too. But this is what, so if I'm using the advection dispersion equation, if I'm given flux data, flux concentration data, I divide this by m over q, make it a probability density function, find the numerical first and second moment, equate those to L over V and this quantity, and I find D and V. This is my estimate using method of moments of these model parameters. Okay. So one of the things that I'm going to note, which I also want you to observe, is look at the travel time variance. This is the variance of the travel time, the variance of this distribution over here. Okay. That increases with L linearly. So as the distance increases, this thing is spreading linearly. Okay. So we'll keep that in mind for a minute. So this was, of course, we did all this because we believed in this model. We believed that advection dispersion equation exists. I did not have to fit this because now it's a PDF. I don't have to actually fit the ADE, or what is called as a Fickian PDF in this case. Professor Guha talked about log normal distribution. I could go ahead and fit the log normal distribution to it. He talked about the gamma distribution. I could fit a gamma distribution to it too. Okay. Basically what I'm observing is simply the travel times. Okay. Let's say, so advection dispersion model was one model. I have another model, the simplest model that I can think of to start with, piston flow. Okay, that means no dispersion. So it assumes that all particles, so it's a sharp front model, all particles are traveling with the same velocity. Okay, each of them has a velocity of v. Okay. All of them. So if I had introduced those 1,000 particles, all 1,000 particles would be traveling with a velocity of v, effective velocity of v. They would all come out of the soil column at one particular time. At all the other time intervals, you'd be getting 0 particles. Right? For that, the travel time distribution is simply delta of t minus L over v. That means when t is L over v, this quantity is 1, rest of the place is 0. Okay? The simplest case. So since this is also, then this becomes a travel time distribution. Expectation of t to the power of n by definition is this. Again, by the definition of delta function, it's simply L over v to the power of n. The first moment is L over v. Second moment is 0. There's no variance, there's no spread. All particles come out at the same location. Simplest model possible. Okay. Okay. I want to now talk briefly about another class of models. Okay. We will call them as stochastic-convective models. And here, I'm going to challenge you to think a little differently. So we consider, let's say, a simple soil column as if non-interacting stream tubes. Okay, and we could have random velocities, we could have random, whatever in each of these tubes. So the random travel time through each tube now is L over V, but unlike the piston flow model, the V does not have to be the same in each column. Okay. It could come from some other distribution. Okay. So we could go ahead and basically say then expectation of t to the power of n is going to be this expectation, which now, because V is a random variable, we will essentially get this expression for travel time distribution. So all this is fine. Now, I want to essentially go back and revisit this advection dispersion equation model. Once I had estimated the quantities d and v, if I now asked you what is the travel time at some other distance L, what would you do? So this, go ahead. What is the travel time? So this is the travel time distribution that I observed based on this flux concentration at a distance of L. At some other distance, what would be the travel time distribution? It's the same equation. It's same in the sense that in this model, fortunately you have L or X also as a parameter. You change the value of X, you simply get the distribution elsewhere. If on the other hand, I fitted a log normal distribution or a gamma distribution, so that is valid at X equals L. At some other L, how would I then find out what the travel time distribution is? Any guesses? Usually the simplest answer is the best one. So in the advection dispersion equation, because it comes from, we did control volume analysis and had space and time dimensions and so on, L actually, or the distance in the column X, appears in the equation. If I fit a log normal distribution to the outflow curve, or if I fit a gamma distribution, what should I do? So how do I make it useful, for instance, for other distances if I want to know what the travel time PDF is? What should I do? What should I do if I change my velocity? Should I redo an entire new experiment? In which case, it's not very useful. We want to have some predictability with these things. Okay. So I want you to think, remember I said t is a random variable. Okay. So let's say when I did my experiment first, my length of the column, and let's say I'm going to call this as my reference. So let's say I make that as L sub 0. That was my length of the column. And therefore my random variable that I have t, which essentially denotes the random variable for the travel time through this column, let's say I call that as t sub 0. Okay, that's my random variable now, because it was done for L sub 0 conditions. I basically go to some other experiment now, and now let's say I choose another length of the column L1, a different length. Okay. What is your estimate of what the random variable will be here? T1. Let's say T1 is my random variable denoting the travel time through the column now which has a length of L1, different from L0. So let's say L1 is 2 times L0. What can you say about T1? What do you expect it to be? Half? Twice. So I changed the column length to 2 times, so I expect the travel time would also increase by the same factor. So indeed, if I think my new column has a length of L1, my first estimate of T1 is simply L1 over L sub 0 times t sub 0. So t sub 0 is a random variable. Since I did the experiment at t sub 0, I have the probability distribution function of the travel time. So my simplest estimate of what would happen for some other conditions, where let's say I have changed the length of the column, is my new travel time distribution is simply a function of the old PDF. And since t0 is a random variable, L1 over L0 is a constant. So I know what the travel time or what the PDF of T1 is. Same for velocities, right? Except it would be inverse. If I increase the velocity, the travel time decreases. But I would have a similar relationship for a different velocity or a different length. So I can essentially do this. Okay? And this is what we are trying to show then, is if I have, let's say, my f sub t was the travel time probability density function where the length was L sub 0. If I change my length to L1, then by simple transformation of variables, this is my definition of the travel time when the column length changed to L1. It's going to be in terms of the PDF when the column length was L sub 0. Okay? Which essentially says the same thing. If the probability of travel time for L1 was such, probability of travel time for L0 is given. For L1, it's essentially going to be scaled by this factor. So it's simply a simple variable transformation. Okay. Then, notice that if L1 is my new length, and I want to find the travel time moments for this new length, I have to do 0 to infinity t to the power of n travel time distribution for this new length L1, which is in terms of the old travel time, and I will get this expression. So this is just simple algebra. Okay. Similarly, if I want to find the second moment of the travel time at that new distance, I can do the same analysis and I'll get a different expression. So these are very simple expressions. But once I find this expectation of t square and expectation of t for this different length, I can find what the variance of the travel time is at this new length. Okay, and that's what I get. So it's L1 over L0 square times whatever the variance was at my reference length. So what this shows is, if I change my length, that means as the column length increases, the variance increases as the square of the distance. Okay, so I want you to compare this to the ADE model, where the travel time variance was increasing with L linearly. So fundamentally, they are two very different models. They come from very different considerations. Can anybody guess or try to estimate why that is so? Because then you'll have to understand what is happening in each model. So there is a fundamental difference. Let me first tell you the ramifications. Okay? The ramifications are first that if I did a column experiment at length L sub 0 and found the flux concentration, I can fit the ADE just as well as I could fit, let's say, a gamma distribution or a log normal distribution, as you will do. They'll all fit perhaps equally well. You would not be able to tell whether I should be using the ADE or whether I should be using a gamma or a log normal, just from that one single experiment. You would very likely have to do another experiment, as in this model, at a different length, find the PDF of travel times, and ask yourself, did the variance increase linearly or with the square of the distance? If the variance increased linearly, then you would say, okay, I think I want the advection dispersion model. Anything else? You would say, I'm not sure if advection dispersion is the correct model for this. But with one experiment, you are not able to tell. Okay. So now let me come back to the question. Any thoughts on why? What's the fundamental difference between when we do advection dispersion equation? Like I said, we are saying some things about what is going to happen to the concentration. When we did this travel time distribution thing, and I showed you the cartoon and said, well, particle enters, it goes wherever, it comes out wherever else, it's doing something else. What is the, any thoughts? Because then you would say, now I actually have insight into what happens into solute transport. There are two different ways of thinking also. This is something that we do in fluid mechanics, but in fact, it's actually the same thing. We talk about Eulerian and Lagrangian approaches, right? And they come from different considerations. So it's the same idea actually, the same difference fundamentally. The advection dispersion equation uses control volume, it's an Eulerian approach. The travel time distribution, each particle is being tracked individually, it's a Lagrangian approach. Okay? and therefore they're going to be different. They're not going to be behaving the same way. So the question about why you think one should have a different variance. So let me try and explain it. At least I'll hand wave so that you have some idea. In the advection dispersion equation, when we do this, we assume Fick's law. Okay, Fick's law, what it does is, if concentration is higher next to a location where concentration is lower, it's going to have flux trying to move from the higher to lower to sort of bring them together, right? So it keeps making that adjustment. That is how it's designed. But when I have individual particles, these particles are not interacting. I could have a very high concentration right next to a very low concentration, no mass is exchanging. The high concentration particle moves independently, the low concentration particle moves independently, so you get a much higher spread because there's no mixing that you are allowing in that model. So Lagrangian approaches, which are particle tracking approaches, will give you higher variance than advection dispersion type models. Okay. But this is where the logic comes from. So, okay, I want to quickly talk a little about non-interacting stream tubes because this is going to be your tutorial on day 5. So I'm sort of giving you a heads up on some of these tutorials. Okay. So log normal distribution looks like this. Okay. And if it's non-interacting stream tubes, each of these stream tubes has a velocity which varies log normally. Then this is my expression for its density. If I do the travel time, in each column it's L over V, but when I take expectations, it's V to the power of L over V. Expectation T to the power of N will make it L over N times V to the minus N. V is log normally distributed. So expectation of V raised to the minus some other power is fairly easily obtained. Okay, it's a simple expression because it basically collapses to like the moment generating function for the normal distribution. So expectation of T, variance of T will have, will have expressions that are fairly easily available. Okay. Oh, that was my last slide. First, let me stop and see if you have any questions. Okay. Well, let me ask you some questions, and I want you to think about those. In your, in your tutorial today, you will essentially look at this data and you will essentially fit using method of moments, advection dispersion model. You will fit gamma distribution. You will fit log normal distributions, and using using this idea over here. Using each of these distributions, you will essentially figure out what the travel time distribution is at some other distances. So the reference column, the data that you are given for a column of length 100 centimeters, you will find out what it is going to be like for 200 centimeters, what it is going to be like at 50 centimeters. Okay. For the ADE model, you will essentially do it using this method. That means you are treating the ADE model as a stochastic convective model. But as I said in the ADE model, I don't have to do this. L is actually a parameter already. I can use the ADE model and find the PDF at a different L without having to resort to stochastic convective ideas. Will they be the same? Well, you'll find out. That's part of your tutorial. Something else to think about is when we have these models, like the advection dispersion equation model, which is over here, or like the log normal distribution, which has two parameters, mu sub y and sigma y, but they don't tell you what L is. Or you have the gamma distribution, and depending on how it's defined, you have alpha and beta parameters. What makes these models stochastic convective models? Are they all automatically stochastic convective models, or what properties must they have, or what properties must the ADE model have so that it will actually become a stochastic convective model? Because we said, hey, this seems fairly intuitive. Our models should do this. This is not like very difficult. But if they're not, what does it take to get them there? So something else for you to think about. Okay. Any questions?
As far as the travel time is concerned, only negative mark can give you a better thing.
No, what I'm going to, and I think your question is also sort of anticipatory in the sense that we'll be talking more about this today and perhaps tomorrow. If you are given travel time distributions, okay, you are able to compute temporal moments because you just have a curve in time. That's all you're given. With temporal moments, you essentially get this. Okay. And I think, what was your question again? Let me.
So the question is, our main interest is to find the temporal moments of the flow model. So as per your discussion, is it only Lagrangian model can give a better
Okay, right. So okay, now I do remember your question. So what I'm going to say is, if you are given CF, this is what you have observed, then you can only use Lagrangian techniques. You can only calculate your model parameters using Lagrangian-based descriptions. What we will talk about today is, we have talked about travel times, and again, like I said, we are anticipating. I'll talk about travel distances, where we will be using, instead of the flux concentration, we will be using either the bulk concentration or the resident concentration along the column. That allows us to analyze it in an Eulerian sense. And you can basically look at that and do some similar things, but we will see how they compare with each other. Then you would use Eulerian techniques. So it's a good question. We use temporal moments when we have data of that nature. We use spatial moments or other moments, but we haven't talked about those yet. Right now, we have only talked about the Lagrangian framework. So today afternoon, or next lecture, we'll talk about depth moments, which will begin to address that question. Any other questions? All right, we are almost 10 minutes ahead, so we'll have a longer tea break then. All right, thank you.